Right now we're looking at lesson 2.6, which is all about special functions. We're going to look over about 4 different kinds of special functions that, well, some that we have seen, some that we haven't. This will more be just kind of identifying them, noticing where they're at, and kind of how to use them or work with those, both the equations and the functions and the graphs themselves. Okay, so we're going to look at step functions, constant functions, and the identity function first. Now a step function is going to be the new one for us. Okay, so a step function, it might be easiest to explain this one using an example. So for our example, we're going to be looking at one psychologist charges for counseling sessions at the rate of $85 per hour or any fraction thereof. So draw a graph that represents this situation. So as you go into the psychologist, they are going to charge you, so if you're there for, let's say, exactly 0 hours, you should pay exactly $0. No hours, no dollars. You shouldn't have to pay them. Okay? That should make sense. Okay, that should be nice and easy. But if you're there for just a little bit, okay, just a fraction of an hour, now all of a sudden they have to charge you $85. So if you're there for just 1 second, 1 minute, 2 minutes, 10 minutes, 30 minutes, any fraction of this hour, you're going to have to pay them that $85. Now, it's no more, no less. It's 85 all throughout, right up until this 1 hour. Okay? After 1 hour, it all of a sudden jumps up to 85 more dollars. Now, 85 plus another 85 is going to be 170. So all of a sudden, you're going to be up here. Now, I'm going to put an open circle here, because if we're exactly on 1 hour, you're only paying 85. This open circle right here means we're not paying the 85, but that's where it starts. So for any fraction of 1 hour, you'd be paying $170 all the way throughout. I'm going to draw a straight line throughout right up until this 2 hour mark. So notice this open circle, I should also have one right here. Okay, so for any, if you're at 0 hours, you should pay $0. But anything above that, you start having to pay that $85 for, again, 1 minute, 2 minutes, 10 minutes, 30 minutes, 40 minutes, 59 minutes, 1 hour exactly. You're paying $85. Anything even just a little bit after 1 hour jumps up to 170, and you're paying 170 for 1 hour, 1 hour and a half, 1 hour and 40 minutes, 1 hour and 45 minutes, anywhere in here all the way up until for 2 hours. Okay, even though down here you weren't there for a full 2 hours, it's a fraction of it. So it kind of rounds it down there. So it says this 2, even though it's not a full 2 hours, you still have to pay that amount. Okay, so this graph, all of this is the same, all of this is the same. Anything after 2 hours, they count it as 3 hours. So you'd add another 100, or you'd add another 85 to that 170, and all of a sudden you'd be at 255. So somewhere up here, all the way across until we get to 3. So notice, as this moves up, it kind of looks like a step. That's where this term step function comes from. Now, things I want you to kind of write or make a note of, again, this open circle at the far left means that's the lowest thing. It's going to get really, really close to that, but not included to. So right up to, but not including. Same thing if it went all the way over and put an open circle here. It'd say right up to, but not including this number. Okay, so it's kind of like our inequalities, up to, but not including this spot. Same thing with a filled in circle, right up to and including this number. So notice that we went right up to and including 1 hour, all costed $85. Okay, once you hit 1 hour, that's still at $85, everything there. But if you jump ahead then, everything within here doesn't include this 1 hour, that would only be 85, but anything past that. So not including 1, but anything beyond it is now going to be that 170. Okay, so open circle doesn't include, closed circle does include. So that situation, that example of the psychologist or any doctor or somebody that you go see for so many dollars per hour, that should help make sense of what a step function is and what it looks like. Now, when we're graphing our own step functions, this is actually called the greatest integer less than or equal to. It always means to round down to the nearest integer. You might also call it the floor function. It can be written like this. You can see there's kind of the kind of squared off bracket with two bars. Notice the double barred bracket. Or you can write it with a regular L and a backwards L going underneath. That lets us know that it is a floor function. Basically what this is saying is take your answer and then round it down to the nearest integer. If we didn't have these things underneath, if it was just the bars, remember that would be like an absolute value, which says take your answer and make it only be the positive version. These are saying take your answer of what's inside here and then round it down. Before you can graph these, always make a table. Anytime you see either this double bar piece or these L's, the regular and backwards, that is a floor function, always make a table to help you figure out what it's going to look like. How do you know what pieces to use here? Well, you can really use any x values you want and as many as you want, but do enough values that you're going to find a pattern. Now again, I'm going to go through and show you what the regular one looks like. If we have y equals the floor function, or our greatest integer less than or equal to x, basically what that's saying is if we plug in values for x, we just round it down to the nearest integer. So if you plug in 0, round that down, it's going to be 0. 0.1 rounded down is 0. 0.5 rounded down is 0. 0.9, you're always rounding down because it is a floor function. So 0.9 rounded down is still 0. So notice these four pieces, that happens right here. 0.1 happens about here. 0.5 is right in the middle. 0.9 is right here. We're always rounding down and getting this flat step. It's not until we reach this spot where x is 1. We plug it in. Now all of a sudden it jumps to 1. Notice the filled in box or filled in circle right here at 1. Okay, we finally jumped up there. And at 1.7, so 1.7 I guess would be here on our x value. We're still at 1 for our y value. So it still makes that straight line as it climbs its way up. It's not until 2, when x is 2, that y would be 2. That's when we make that next jump. So again, it's just going to be climbing up, making these stairs or the step for our function. Now again, we would say these open circles and closed circles kind of have to match up. Because what it's saying is once you reach 1, that's when you jump up. Once you reach 2, right here, that's when you jump up. Once you reach 3, coming on over right here to 3, that's when you jump up. Now that helps us because that keeps this an actual function. Remember, all functions will have to pass this vertical line test, or if you put up a vertical line, it can only hit 1 point. Okay, can't hit 2. Now if I place it like this, it might look like it's hitting 2 here and here. But that's why this is an open circle saying it's getting really, really close to that spot, but never touching it. Once we touch this line, once we're actually plugging in 3 for x, it jumps up and is only touching right here. So that's what makes this still a function. Okay, so now that you've kind of seen what this step function looks like, that'll make it easier for plugging in your values here. Now in our function, the equation is the floor function of 0.5x. What this is saying is take any x value, multiply it by 0.5, or take a half of it, and then round it down. So if we take 0, take 0.5 times 0, well, you get 0 still, and then you round it down, we'll end up at 0. So 0, 0 is going to be one of our spots. Same thing, if we plug in 0.8, well, times this, that 0.5, or half of 0.8 is 0.4, and then we round it down, and we get 0. To make this a little bit more clear, Off to the side, I'm going to write what they were just after multiplying 0.5. So this one became 0. We rounded it down to 0. This one became 0.4. We rounded it down to 0. That would put us right here. If we take 1 times 0.5, we'd get 0.5, and we would round it down to 0. So 1 is still here. Notice we haven't jumped up yet. If we take 1.8 times it by 0.5, and we get 0.9, round it down, and we still have 0. So notice this one goes all the way over here. As we slowly approach 2, though, if we plugged in 2, 0.5 times 2 would be 1. 1 rounded down to the nearest integer is 1. So this is where it would finally make that jump right here. All of these values would work. They would stay at this 0 right up until this spot. So it would be a nice big open circle. So from 0 all the way up until 2, all of those values will multiply by 0.5 and then round down and get 0. If we start with 2 times 0.5, we get 1. Rounded down, it's 1. Let's try 3. 3 times 0.5 would be 1.5. Rounded down, you'd still get 1. So at x is 1, 2, 3, our y value is still 1. Notice, we don't make another jump until where x is 4. 0.5, or a half, times 4 is 2. 2 rounded down is just 2. So it isn't until on our x-axis, way over here at 4, that we finally make the jump to 2. Which means this one is going to come straight across until this spot right here. Similarly, this one will come straight across and come off the screen over here till its next spot. Okay? Now we didn't plug in any negative values. We could though, and we would get this. It would continue the same exact pattern, and all of these steps would be 2 units long, and then they would just drop down 1. Yes, technically they would have an open one and this one way over here. So this would be the graph for this floor function, or this step function, as we move up. Again, to find these patterns and find these graphs, just make a table and do enough of the values until you see the pattern. Then you can just continue the pattern a few times and graph out your floor function. Okay, so we're going to try another floor function. I took the exact same table that we had before from this one, the original. So y equals the floor of x. And this one says take that floor function of x and then just minus 2. So really, all we're doing after we round down our answer, we're just taking 2 away. So 0 minus 2 would be negative 2. 0 minus 2 is also, oops, that negative 2. This 0 minus 2 is still negative 2. Negative 2. 1 minus 2 would be a negative, oops, 1. This one would also come out to a negative 1. Once we reach 2 here, 2 minus 2 would get us to 0. So basically this function should graph out just like this, with all of these being 2 less. So this piece should actually start down here. It'll look something like this. I'm going to use red this time. Where x is 0, we round it down to 0, and then subtract 2. Gets us down here. Where x is 0.1, just a little bit here, we round it down to 0, subtract 2, we're right here. Where x is 0.5, we round it down to 0, minus 2, we get here, and it's going to give us a graph that looks a little something like this. Open here, filled in here, all the way to open here, filled in up here, and it's going to continue that pattern all the way throughout. It'll also go in the other direction. Again, you can plug in negative values on your table to find these. It'll work the same. But I just want you to notice something interesting here. I can take this whole graph and move it down. Notice that this graph still fits the same as this one. Our original y equals the floor of x function. Notice where everything is. That's where this one is. But all of those things just got moved down 1, 2 spaces. And that's where our graph is. Got moved down 2 spaces. So that would be our step function, or the greatest integer less than or equal to function, or you can call it the floor function. The floor function is probably the easiest way to say it. We're going to go over a constant function as well. Constant functions are really easy because for any function or any f of x, you can just replace y. So for a constant function like this one, y equals -3, it's really, really easy because we know how to graph a y equals. It's just a horizontal line. All the y values at -3. If we wanted, let's say, I'm going to do this one in green. This would be another constant function. It's called constant because there are no variables over here. There's no x that goes along with it. This is an f of x. There's no x over here, just a number. So what if I had y equals 8? In that case, I guess we could call it f of x equals 8 to keep it in our function notation. Well, we would just do, I'm going to get green here, we would just put a straight line right across at 8. Okay? In this way, we can notice that a constant function is just a horizontal, flat, straight line. Okay? Any constant function will just be f of x equals some number, and it'll graph a straight horizontal line. The last one we're going to look at in this video is called the identity function. This one is essentially a mirror. There's only one identity function, and it is right here. F of x equals x. It's called identity because whatever you plug in is exactly what you get out. So it's the same as saying y equals x. If y equals x, we can just plug in some points for that, or some values, and see what works. If we plug in 0, we get out 0, so 0, 0. If we plug in 1, we get out 1. If we plug in 2, we get out 2. If we plug in 3, we get out 3. If we plug in 4, we get out 4. Same thing in the negative directions. If we plug in -3, we'll get -3. If we plug in -8, we'll get -8. So this is what that line will end up looking like. It's just a straight diagonal line. Starts at 0, 0. And it goes up 1 over 1, up 1 over 1. So it's got the equation y equals x. Again, it's called the identity function because whatever you plug in is what you get out. And it makes this line. That'll cover our first half of 2.6.